In this video on proton NMR, we're going to look at how D2O affects an NMR and how you can use it to identify certain functional groups. And we'll also go through a couple of exam style questions related to that as well. So what is D2O actually used for? D2O is basically the deuterated form of water. So imagine H2O, but instead you replace the hydrogen with deuterium, so D2O. You can use it to identify OH and NH protons by something called proton exchange. So the deuterium exchanges with the hydrogen. Okay, and if you do that in proton NMR, it can have certain effects. Now, the labile protons, which means easily removed protons, can be exchanged. So think about it as anything that's acidic, you can find the deuterium will exchange with that proton. Okay, now you add the deuterium oxide to it and you get certain changes. And we'll have a look at it to start off with. So an alcohol, if you add D2O, will go to OD. So you'll change the H to a deuterium. Amines will do the same. Okay, carboxylic acids will do the same. Amides, again, the same. And then phenol, because phenol is slightly acidic as well and is a kind of a functional group that has an OH in it, okay, will also change. And that's all if you add D2O, okay, because it does this proton exchange. Now, if we look at an actual example, and we've taken the carboxylic acid example out of there, and you've got a peak here for your carboxylic acid. If I then rerun that NMR and I run it in D2O, the following will happen. Okay, the deuterium will exchange, and then that peak, which has now gone green, will just disappear. Okay, now this peak disappears as the deuterium cannot be seen in proton NMR. Okay, hydrogen can, deuterium cannot. Okay, so it disappears. So if you see any peak disappear, you know it's one of these functional groups that we have. Now let's go back to the functional groups and remind ourselves. So we're looking at D2O being added to any of these, and it will cause the peak that you see here on the NMR, okay, will disappear. So if I, for example, have an OH peak and I think it is a phenol and that disappears, well, I know I've got an OH peak. Okay, if, for example, I've got an alcohol and then I add D2O and the OH peak disappears, well, again, it just adds to the evidence. So you just have to say in the exam that I believe it is an alcohol or I believe it's a carboxylic acid, and the evidence for that is the fact that the peak disappears as deuterium cannot be seen in the proton NMR. We're now going to move on to exam style questions concerning creating a table and doing an MCQ. The first one is to do with tyrosine. Now, normally they give you 3 different structures and normally they are amino acids. So you can see one structure here is done structural formula, another one structural formula, and they do that to make it more difficult. And they often also do skeletal at the end, especially when it's got benzene in, to make it more difficult. Now, they've shaken the tyrosine with D2O and they want to analyse it with HNMR or proton NMR. You've got to predict the table. So let's move it across. Okay, and let's look at the table. So the table is chemical shift, relative peak area, splitting pattern. That's really important because you've got to analyse this structure to get that. Okay, so let's look at the protons that we don't think are going to do anything with D2O first. Okay, so first of all, the benzene. The benzene attached to the OH, which is a phenol group. Okay, they're not going to do anything. Then we go for this CH2. It's important you know that the 2 hydrogens coming off there. Remember, skeletal, 4 bonds to a carbon. Therefore, if 2 bonds are already used up, there's 2 bonds left which go to the hydrogen. Okay, now CH on the next one. So we've got a CH, a CH2, and a benzene, and they're the ones we're going to do. Now the next one we're going to highlight are the labile protons. They're the ones that are liable to move. That includes 2 sets of acidic protons and a basic proton. So we've got 2 acidic ones, which is the phenol, OH, and the carboxylic acid, and then we've got a basic NH2 here. Now they're all labile, they're all on your list that I told you earlier. So if that's the case, we do not do those. We do not put those into our table. So they're looking for you to not put those in the table to get the mark. You've only which means this is much simpler than it looks. There's only 3 peaks for you to do. So we're going to do the benzene one first. I've just looked at my data sheet. I've taken the range from the data sheet. I've counted the number of protons, and I've said it's a multiplet because I don't have to do the splitting on benzene. We're then going to go to the CH2 here, okay? Now that is going to come out, this CH2, between 2 and 3. The reason I know that is because the CH2 is bonded to a benzene. If you look at your data sheet right now, there'll be benzene with a C attached to it with an H that comes out between 2 and 3. And then you've got a CH bonded to an N. Well, that also comes out between 2 and 3. I just want to discuss the doublet and the triplet to finish off, because we know there was 1 hydrogen there, 2 there, so this relative peak area is fine. Now the doublet. The CH2 here, there's no hydrogens on this adjacent carbon, and there is 1 hydrogen on this adjacent carbon. So N plus 1 is, there's 1 hydrogen on the adjacent carbon plus 1 is 2, and therefore this peak here will be a doublet, and that's where I got that from. This one, okay, there's no hydrogens on this one, and there's 2 hydrogens on this one. So again, N plus 1, 2 plus 1 is 3, so therefore you get a triplet. And that is how you can do a simple table, which you may well get in the exam, okay, from a rather complex looking molecule shaken with D2O. We're now going to do an MCQ, and in this MCQ we have a molecule where we have to use carbon-13 NMR knowledge, proton NMR knowledge, and the fact that D2O is put in as well. Let's put the writing over here, centralise our molecule, okay, and we're looking at the carbon-13 NMR first. Carbon-13 NMR, the bit you need to be aware of is the fact that benzene, you have to look at the different peaks in benzene in carbon-13 NMR. You don't have to in proton NMR. So basically here, are any of these carbons equivalent to each other? Well, there's no symmetry anywhere. So that means there's 6 carbons in the ring, so I'm going to get 6 peaks in my carbon-13 NMR. Now if I then count along and I go, there's another one there because there's no symmetry anywhere, and I'm just counting the carbons here. So 6, 7, 8, 9, okay, in fact let's write it probably, so 6, 7, 8, 9, okay, and then we'll go 10, 11, 12, 13. Okay, so we've got 13 different peaks. Okay, so instead we've got 13, so therefore that one is wrong. It's not 8. Now, you might say, where does the 8 come from? So where do they do that? Because they always put an answer which you may get. And it's because you might get confused between proton NMR and carbon NMR and just think this all comes out as one carbon NMR peak, just like it would do if it was proton NMR. Okay? So, if we then take this off, okay, and we start looking at the next one. So we're just highlighting there the proton NMR instead. Okay, so proton NMR is going to look at all the different protons that we've got. So first of all, we've got a signal here because we've got an OH. So, and then we have again H is here. None of them are in the same environment, and we don't have to care about the different environments for proton NMR anyway. Okay, so this will just come out as one peak, which will be a multiplet on our NMR. And then we'll go there for the CH2. Again, no symmetry anywhere. 4, 5, 6. Now here's the important thing. You are going to include the NHs and the OHs there, because this is basically NMR without D2O. So 7, 8, because there's 2 hydrogens there, 2 hydrogens there, 9, and then the hydrogens here will be 10. Okay, so we've got 10 peaks. Remember, this benzene will all come out as 1, but it only counts as 1 in proton NMR. So that means we're going to get 10 here, so that one is correct. Now we just want to think about this in terms of D2O. So all we can then do, okay, is take out the peaks that are D2O. So phenol, that's a D2O one, so that's gone. Okay, an amine, that's D2O one, so that's gone. An amide, that's D2O, so that's gone. So I've got some confusing numbers here, but okay, let's see if we can work. With this. Okay, let's get rid of that and that. So that will be we put that as 1. So 1, 2, 3, 4, 5, 6, 7. Okay, so we've got 7 different protons. We've got the whole protons from the benzene and the protons from all the carbon chains, but we are not including the protons that are labile in the amide and the NH2, and that is because they are being washed in D2O and they're being exchanged. So that means with D2O there are 7 peaks, okay, and therefore that is correct. So in this question, D2O does have 7 peaks because you've eliminated the amine, the amide and the phenol. In this video we've looked at D2O and how it affects proton NMR and some exam style questions related to that as well. You can also see D2O being used in our combined techniques videos, which combine NMR, mass spectrometry, IR and some elemental analysis.